In section 10.6, we're looking at segment lengths in circles when we're talking about chords and secant segments and tangent segments. In this first theorem, and an example right away, we're talking about segments of chords. If you have two chords intersecting a random place in a circle, the product of the lengths of the parts of the chords are equal. Now, product tells you to do what? Product tells you to multiply. So if we have two chords intersecting or crossing in a circle like we do here with these two red chords, then if I multiply or do the product of the lengths of the parts of each chord, they're equal. So I'm looking at this one chord and I say, well, obviously it's split into two parts now because of the other chord. If I multiply the two parts together, product of the lengths of the parts, it should be equal to the product, or when I multiply these two parts together. So I'll look at my first chord. How about I do this in blue, actually? Multiply the two parts, so 4x times x. Okay, and that should be equal to the product of the parts of the other chord. Here I have an x plus 1 and a 3x for the two parts. Okay, now hopefully if I write it like this, you'd tell me I'm doing something wrong because I'm doing x plus 1 times 3x. This is a quantity, there's addition there, so I got to have parentheses. Alright, let's simplify, let's solve here. What's 4x times x? Well, that'd actually be 4x squared. That equals, on this side, x plus 1 times 3x, I got to distribute. 3x times x is 3x squared. 3x times 1 is just 3x. Alright, a lot of what we're doing today is going to bring us back to stuff we did in algebra with quadratics. Remember, quadratic means you have x squared like we do here. Now, typically with quadratics, unless there's an x squared and no x term, there is an x term here, but generally with quadratics you get equal to 0 and you try to factor. Now, factoring could mean factor out from both terms. Factoring could mean double bubble. If you remember, we called it double bubble, finding two binomials that would multiply. So I'm going to get this quadratic, because of the x squared, equal to 0. So I'm going to subtract 3x squared from the 4x squared to move it to the other side. Again, we're trying to get equal to 0, so I'm also going to subtract 3x so that there's nothing on the right-hand side, it's just 0. And 4x squared minus 3x squared is just 1x squared. I also subtracted 3x on this side. And now this equals 0. Why did I get equal to 0? Why do I do that with quadratics again? Because if you factor, you're finding things that multiply. Okay, you're doing the opposite of distributing, or basically finding things that would multiply to 0 is important, because the only way to multiply to 0 is if one of those things were actually 0. Okay, so factoring in this case, since it's just an x squared and an x, I can take something out or factor out of both terms. I can factor out an x. Now, we know factoring is the opposite of distributing. We're dividing out of both terms. X out of x squared is just an x remaining. X out of negative 3x would be minus 3. At this point, we have x times x minus 3 equals 0. And again, to multiply to 0, one of the things has to be 0. So either just the x is 0, which is not correct. I mean, x can't be 0. That wouldn't be good because these segments would all be 0. But here's the interesting one. What number minus 3 would be 0? Well, 3 minus 3 is 0. And that'd be the interesting answer. I'm going to cross out that 0 answer. That doesn't make sense. But x is 3 in this case. And let's see here. What would all these segments be? If this x is 3, this would be 3 plus 1, or 4. This would be 3 times 3, or 9. X is 3. 4 times 3 is 12. And let's check, is the product of the parts of the chords equal? Well, 12 times 3 is 36. 4 times 9 is also 36. Okay? So two chords randomly intersecting in a circle, multiply the parts of their chords, and those should be equal. And we're going to have some more quadratics today as we move on. A little vocab term here. What is a secant segment? Now, you know a secant is a line that goes through a circle and hits at 2 points. A secant segment is just not a line that goes on forever. So it's a segment that contains a chord, like this red one is a secant segment, because it does go through the circle, but only on one side. It contains a chord, which is this part of it, and it goes to an endpoint outside of the circle. The blue line is also a secant segment. It's got this part as the chord, but it does extend to a point outside the circle, making it a secant segment. And then when you talk about the external segment, external means outside, right? So the external segment is a part of the segment outside the circle. In this case, for the red one, here is your external portion. It goes from that point outside just up to the circle. And in the blue secant segment, here's your external portion. It goes from that point outside to just where it hits the circle. Okay, again, external means the outside portion. Now the theorem that we're going to talk about, and talking about the segments of secants, is that if you do have two secant segments sharing an endpoint outside the circle, like I do here, right, two secant segments, they share an endpoint outside the circle, then the product, again, product means multiply, of the lengths of the full secant segment and the external segment are equal. So if I multiply the full segment and the external segment, they're equal. Now, if I was doing the red one, there's the external part, but I also need to multiply by the full segment, which would be that whatever that entire length is. And then for the blue one, length of the full secant, which would be this entire length, total up whatever those two portions are, times just the external part. So, writing this out in words, if you knew whatever the full length was, maybe it's 15, times the external part, maybe that external part is only 10, then that would have to equal whatever the full times external is for the blue one. So if you have two secant segments, full times external is always equal for both. And just a slight difference, let's say you have a secant and a tangent segment. Hopefully you can look at this and tell me which one's which. The blue segment is called a secant segment, right? Because it does go through a circle at 2 points, but only on one side. Now, with the secants, we just talked about this. With the secant, you do whatever the full length is times the external part. But this red guy, this is a tangent. It's a tangent because it only meets that circle at 1 point. Now, we're still going to look at products. We're still going to multiply. But if we have a secant and a tangent segment, then the product, or when you multiply the full secant segment times the external part, it actually equals the square of the length of the tangent. And the reason why, if you think about it, the full length of a tangent is the whole red segment. And the external part of the tangent, well, a tangent is all external, so it's really like full times external is like the same thing times itself, and when you multiply something by itself, it is squared. Okay, so in this case, let's say we have the one secant, well, you're going to do full times external again, but in this case, it's going to equal, instead of a tangent being full times external is the same, you're just going to do the tangent squared. Sorry, I gotta move this over so I have a little more room. But you would just take the tangent squared, and those things are equal. So let's look at some examples. Again, we're going to see some quadratics coming up with these. Alright, excellent first example here. These are both secant segments. Now remember, with a secant segment, you're supposed to do the full length times the external part. And here's the tricky thing. What is the full length here? What would I do with 3 and x to get the entire length? Well, maybe you're not totally sure, but let's look at the one that we have both the numbers first. How would you get the full length of this secant segment? This much is 4, this much is 2. Wouldn't you tell me the whole length is 6? And what did you do with those things? You added them up, right? So keep that in mind when we do this one. The full length here is 6 times, what's the external portion of the secant segment, will be 4. That's the part that's outside the circle. Now that should equal, okay, what did we say we did to get the full segment here? We added 4 and 2, so here I'm going to add 3 and x. So 3 plus x is the full thing, times what's the external portion of this segment would be 3, because that's the part outside. So full times external. Now hopefully you're thinking, hey, if you're going to multiply those, you better put parentheses around that quantity with that addition there. 3 plus x is one thing, times that 3. Alright, let's go to solve this. On this side, it's just 6 times 4, or 24. On this side, I will distribute. 3 times 3, 3 times x, 3 times 3 is 9, plus 3x. Get x alone, I'll subtract 9. And I get 15 equals 3x, right? Subtracting 9 goes over there. Divide by 3. 15 divided by 3 is 5 for my x value. And that seems like that could be pretty reasonable. Okay, so secant segments, I did the full thing times the external part of it. Keep in mind I had to add to get the full length. What's going on here? Here I have a secant segment, which I know is full times external. But this is a tangent. Now with a tangent, you're just supposed to square it, right? So it's a tangent squared, and for the secant segment, I'll do full times external. Well, the tangent is just x, so that's just x squared equals, oh, the full thing. For that secant, the full thing would be 20 plus 16. The full length is 36 then, right? Times the external part, or the outside part of the secant, is 16. X squared equals, what is 36 times 16? It's 576. And now, this is x squared. How do you undo squared? You take square root. I think this is a perfect square. And it is. I find out that x is a length of 24. Does 24 just seem like a decent answer? Yeah. Okay, so there we had a tangent in a secant segment. Oh, and then here, this is where I have two chords. I always like the two chords one. It seems a little bit easier sometimes, because really you just multiply the parts of the chords together, and they should be equal. So this chord has parts of x and 3, so I will just do x times 3. Well, a better way to write x times 3 would be 3x, or 3 times x. And that should be equal to what I get when I multiply these two parts. So 4 and 6. 4 times 6 then. 3x equals 4 times 6 is 24. Divide by 3 and x equals 8. And that seems reasonable for that length. Okay, let's try some even trickier ones here. I'm going to get some quadratics here. Alright, I've got a secant segment. I've got a tangent segment. With the secant, remember that you need to do full times external. And that should equal, well, if the tangent, you just take the tangent squared. Alright, what's the full length here? What would you do with 10 and x to get the entire length? You would add them, wouldn't you? So I'm going to do x plus 10, that would be the entire length. It's a quantity, I better put it in parentheses because I'm multiplying by the external portion. And actually the external portion is x, right? That's the part that's outside of the circle. And that equals the tangent length squared. The tangent is 12, so 12 squared. Here I need to distribute. X times x is x squared. X times 10 is 10x. And that equals 12 squared. 12 squared is 144. Alright, at this point, notice I have a quadratic because I have x squared, I have x squared, I have an x, I have a number. With these quadratics, get equal to 0 so that you can then factor and find things that multiply to 0. So in this case, x squared plus 10x, I'm going to get rid of 144, make 0 on the side by subtracting 144 from both sides. So subtracting 144 over here, and now there will be nothing on the right. Think back to last year. This is a full quadratic. We're going to do that double bubble type thing, or find two binomials that would multiply to give me this trinomial. To get that x squared, I would have had x times x. The numbers that go here are going to multiply to negative 144. And I know to multiply to a negative, I need one positive number and one negative number. And I'm trying to think what multiplies to 144, but since there's one positive and one negative, they have a difference of 10. They're 10 numbers apart, basically, and the bigger number must be positive since I want positive 10. Well, I know it's not 12 and 12 because that's the same number. I was thinking, let's just divide by 4 maybe. 4 and 36 multiply to 144, but that's not a difference of 10. Let's divide by 8. Hey, 8 times 18 is 144. And that is a difference of 10. Now I'm positive 10, so I'm going to make the 18 positive 18x, notice. And a negative 8x would have given me the positive 10x. We are multiplying to negative 144. At this point, I can determine what x equals, because these things multiply to 0. One of them has to be 0. The x that makes x plus 18 equal to 0 is negative 18. And I don't think that that length can be negative 18. So we're crossing that one out. But the answer here will be the correct one. What number minus 8 is 0? Well, 8 minus 8 is 0, and then these things will multiply to 0. I'm looking at an answer of x equals 8. And that seems reasonable for that. Alrighty. One more example on this slide is dealing with two secant segments. And remember, with secant segments, you always do full times external and set those equal. This will be a good one here. What is the full length? This much is 3, this much is x plus 2, and what do you do with those two things to get the whole thing? You add them. So 3 plus x plus 2. Combine like terms. It's actually x plus 5, isn't it, combining the 3 and 2? So for this one, the full thing is x plus 5 times the external, and the external part is the part outside, which is 3. Quantity, put in parentheses, x plus 5 whole thing times 3, equals, I need the full length here, which I would take these two parts and add them together. So x plus 1 plus x minus 1. Let's simplify, combine like terms here. X plus x is 2x. Oh, positive 1, negative 1 is nothing. I guess the full length is 2x. Times the external. And for this one, the external part is x plus 1. And since I'm multiplying by quantity, because there's an addition there, I'm going to put in parentheses right away. Alright, distribute on both sides. Here I get 3x plus 15. On this side, 2x squared plus 2x. Once again, I have a quadratic because I have an x squared, and this is my only x squared. I like that it's positive, so I'm going to get these over to the other side and get everything equal to 0 so that I can solve this quadratic. I'm going to subtract 3x from this x term. I'm going to also subtract 15 over here. So now I do have this quadratic equal to 0. I have 2x squared, a positive 2x, and negative 3x, which is minus x, and minus that 15. And now, let's try to factor. Okay, double bubble, see what two binomials multiply to this trinomial of 2x squared. Now it's 2x squared, so it'd have to be 2x times x. I'm multiplying to a negative 15 with the two numbers I put here. So I know one's positive, one's negative, but keep in mind that where you put these numbers makes a difference here. Whatever number you put here, you're only multiplying by x. Whatever number you put here, you're going to be multiplying by 2x. I need a negative x with those two middle terms, which means they're only one apart. And I'm thinking, well, really, I got what multiplies to 15? It's 1 and 15 or 5 and 3. And I'm leaning towards 5 and 3. And since you need them to only be one apart, I'm going to put the smaller number 3 here, bigger number 5 here, because, notice, I'll get 5x there. 3 times the 2x will make this larger, so then I'll have 6x. And to get a negative x term, I want the bigger of the x's to be negative. So if I make this negative, I get a negative 6x. A positive 5x gives me a negative x. And 5 and negative 3 multiplies to negative 15. So I have factored it correctly. So then what could x equal here? Two options, because these things multiply to 0. To make this equal to 0, when would 2x plus 5 equal 0? I'd have to subtract 5 divided by 2, so it would be negative 5 halves. Subtract 5 divided by 2. When would x minus 3 equal 0? When x is 3, because 3 minus 3 equals 0. And of course, for the lengths of x, it looks like negative 5 halves is not going to work. We'd be getting negative lengths here, so I'm crossing this one out. x equals 3 then. So this length 3 plus 2 would be 5. 3 plus 1, this would be 4. 3 minus 1, this would be 2. Are the full times externals equal? The full thing here would be 8 times 3 is 24. Full thing here would be 6 times 4 is also 24. So looking at these secant segments and tangent segments, I'm going to talk about one more real-life example, and then you're going to finish this for class tomorrow. But I'll get you started here. The space shuttle is positioned 150 miles above the Earth. I'm going to do a really detailed drawing of the space shuttle. Okay, that's real good. It's positioned 150 miles above the Earth, so we're going in a straight line. 150 miles. What's the length of a tangent segment from the satellite to Earth? Oh, a tangent segment would meet at one point, right? So that would be from the shuttle at a right angle, just meeting at one point. So what is that length? I'll call it x. How about? The Earth's radius is 4,000 miles. Oh, okay. So since this is a tangent, remember with a tangent you do tangent squared. The thing is, I have to make this a secant segment, which means I have to go all the way across the circle. Put a dot here for the center. The Earth's radius is 4,000. So be careful here. When you come up with the tangent segment and you need the full length, remember the radius was 4,000. So I want you to solve this for class and see if you can tell me the length of a tangent segment from the satellite to Earth. This is your homework, looking at chords in circles and then secant and tangent segments in circles.